In the previous section, we looked at how to simulate the vehicle itself, an electric vehicle. Now we look at how does that impact the battery state, the state of charge of the battery, and therefore how do we deduce a range, a vehicle range, from all of these calculations. So we've seen how to calculate whether it's possible to develop the desired accelerations. And these calculations assume that we do have sufficient battery power available to supply the motor at every time step. Now that's not necessarily going to be true. There was nothing in the previous simulation that said we couldn't just run this vehicle for thousands of miles because we never checked to see if there was any battery energy or battery power available. Nonetheless, when there is battery power available, the simulation steps for the vehicle were correct. So here, to determine the vehicle range based on battery capacity, we have to simulate the battery as well. And here we're going to do a fairly crude battery simulation, although later in the chapter we'll look at some better ways to do battery pack simulation, and it's possible to combine both. We just don't actually do that. And what we are basically going to do is say that we start the battery at a full state of charge, and we drive until we achieve a minimum state of charge, and potentially you could also include a voltage limit. And when we reach that minimum state of charge or voltage, then however long we've driven distance-wise to that point is the vehicle range. The way we connect to the equations in the previous section, we start with the motor speed. So this is the limited motor speed. And from that we get the limited motor power that is required by the motor. So there is a conversion factor of 2 pi over 60 to convert RPM into radians. And then we have the torque, and we also have a conversion factor of watts per kilowatt so that we get our motor power in kilowatts. Now, strictly speaking, kilowatts is not a standard SI unit. Watts would be the standard unit. However, we're dealing with vehicles where a kilowatt is a much nicer number to carry around because we're probably dealing with anywhere between, say, 0 and 100 kilowatts. 100 would be actually on the very high side for most vehicles, but somewhere in that range. And it's easier to say 100 kilowatts than 100,000 watts. When we calculate the power, if it's positive, then we're accelerating, and if it's negative, we are regenerating. So that if the power is positive and we want to take some efficiency considerations into effect, we have to do it differently from when the power is negative, and that's the biggest difference here. So the battery power is equal to the motor power divided by drivetrain efficiency. So if efficiency is 1, it's simply motor power. If efficiency is 90%, I divide by 0.9, and I get a higher power required of the battery to overcome those inefficiencies. And also we include here something called overhead power, and that's some constant power drain to run air conditioners and infotainment systems and whatever else electronic is on board. And this may not be negligible. Infotainment systems can draw many amps at 12 volts in a standard car, and that translates just to a lot of power. So especially if you're in stop-and-go traffic, your vehicle range may be very largely impacted by the overhead power because you're not getting any motor power if you're stopped, and your entire drain is due to overhead. And by the way, some of the more advanced things people are looking at for controlling electric vehicles is to control things like air conditioners, such that they, instead of being fully on, fully off, they have a kind of pulse width modulated or different speed settings, and so the air conditioner can be turned down a little bit at different times and turned up a little bit so that you maybe lose a little bit of your command authority over cabin air temperature, so it's not quite as perfect as you'd like, but it really benefits your vehicle range and economy. If the motor power is negative, then we are braking or coasting or something like that, and we are regenerating. We are putting energy back into the battery pack, and the only difference there is that we're still drawing an overhead power, but this negative motor power kind of counteracts that and may even exceed that to put energy back into the battery. But instead of dividing by efficiency, I have to multiply by efficiency. So again, if I'm 90% efficient, I can only put 90% of that motor power back. I don't divide as I did up here. So when I'm taking it out, I divide. When I'm putting it in, I multiply. So I kind of get the worst of both worlds in both places. So that's the battery power. Now we are going to make an assumption, which is not a good assumption, but it's a very nice assumption to make to simplify things at this point, is we are going to assume that the battery pack has a constant voltage. It's a terrible assumption. We know from a full semester of battery modeling that this is not going to be the case, that the voltage is going to change quite a bit. But for the first principles, not first principles, but first kind of back of the napkin kind of calculation, this is what we're going to do. If you wanted to be more accurate, you would replace this nominal voltage with a battery pack simulation to come up with an actual voltage instead. But we compute the current. Battery pack power equals current times voltage, and we have to convert again using our conversion factor of 1,000 to get into watts, but we can compute a battery pack current from this. And then we update our battery state of charge using Coulomb counting. And so battery state of charge in percent is the prior state of charge minus battery current times the sampling interval, which we have assumed is 1 second. And then with the normalization factors of 3,600 seconds per hour to compute the battery pack capacity in ampere hours to ampere seconds, and then a conversion factor of 100% to convert the unitless 0 to 1 SOC to a percentage. And finally, we compute the driving range. We extrapolate it from simulating a drive cycle. So our range is the total distance of the simulated drive cycle in miles. We can integrate the profile of velocity versus time to get the distance. And we multiply that by this maximum rated SOC minus minimum rated SOC. So that's the state of charge window of the battery pack that you are allowed to use. And you divide by the actual window that you did use in the simulation. So SOC at beginning minus SOC at end. So suppose you're allowed to use, maybe this year is 90%, that's 10%, and we started at 90% here and we ended at 80% here. Just for example, this means that overall I'm allowed to use 80% of the pack capacity, and this here says that I used 10% of the pack capacity in the simulation. It's an 8 to 1 ratio, so whatever distance I did drive in that drive cycle, I can do 8 times that much to get the total range of the vehicle. And that's it. Now we have some sample code, and it's provided in the appendix, and I will briefly walk you through that in a little bit. But before we do that, I'll talk about it and I'll show you some results. The MATLAB code is broken down into 2 scripts, 2 .m files. The first .m file sets up a data structure that has all of the vehicle data embedded in it. So it has the weights, the ratios, everything. All the characteristics of the vehicle are set up in this data structure. And then that data structure is passed into simvehicle.m, and this is the code that actually executes the equations we've just described over the last 2 sections to accomplish the simulation. So setup simvehicle defines parameters of the battery cell, the battery module, the battery pack, the motor, the wheels, the drivetrain. All of these are stored in structures. Now you could pass not a million, but you could pass all of these variables into simvehicle.m discretely, independently, but it's much nicer to have them organized, in my opinion, in a structure where everything can just be passed as one item instead of a lot of them, and that, I believe, also reduces the likelihood of making errors by typing things in the wrong order, for example. The values in the example code are a rough description of a Chevy Volt, first generation Chevy Volt, operating in a pure electric mode. So this is when you've just plugged it in, you've fully charged, you've unplugged it, and you're driving away. So you're pure electric right now. The gas engine has not turned on. Now these are not exact parameter values of a first-gen Chevy Volt. I don't claim that. The values were gleaned from public information and public speculation, moreover, prior even to the vehicle being released to the public. So even though we have some projects with General Motors, I'm not claiming any inside information at all here. And so the simulation should be considered representative and not actually exactly what you would expect to see. But they're probably close. They give range estimates that are pretty close to what people are reporting in real life as well. So simvehicle.m simulates the drive profile and returns a structure called results, and the results data structure has all kinds of information in it, and you can plot all of this information and do post-processing and learn all kinds of things about how the motor is operating and how the battery pack is operating and so forth. I plot a few different results here. So this is the EV simulator using the Chevy Volt parameters, Chevy Volt in quotes, because it's not quite, it's just approximated, and the US06 drive profile. So a couple sections ago we saw US06 profile, and we learned that despite everything I've been telling you for the last in the last course, the profile is not current versus time. In fact, it is vehicle speed versus time. And now you know that in order to get current versus time, you're going to have an electric vehicle or a vehicle simulator that tries to approximate the speed versus time and then derive from that what current versus time must be. And that's exactly what we did here. So we have this first plot is battery power versus time, and you can see that we are achieving battery power in the range of most of the time between plus minus 50 kilowatts, but spiking up almost to 150 kilowatts at different points in the cycle. We also can extract battery current versus time, which is what we used in simulations previously. And here we see again, we are staying within about plus minus 100 amperes most of the time, but sometimes going up to close to 400 amperes. Now we've made the assumption in the simulation that the battery pack voltage was constant, and it is not. But because we made the assumption that it's constant, these are simply related to each other by that constant factor of power equals voltage times current. If you had a more exact battery model in the simulation, you would see variations, distinctions that would make this current versus time different. So that tells us some things that the battery might be able to do. So a peak rate of somewhere in the neighborhood of plus minus 400 amperes, maybe more in the discharge than on the charge. For this drive cycle, of course, we'd want to look at many drive cycles to see overall the statistics from all of them, but this gives us some idea on whether the battery pack can achieve this current profile, this drive cycle. We can also look at motor demanded power versus time, which is very exciting, but what might be more exciting is a histogram of motor demanded power, which shows on one axis the power demand, and on the other axis how often, relatively speaking, that amount of power was demanded. So zero power was demanded, or close to zero was demanded more often than any other, but we also see a skew that most of the time the demanded power is positive, so I'm trying to accelerate or overcome some drag, but occasionally, and not that occasionally, but at sometimes we have negative power, meaning that I can regenerate and get some of the energy back into the battery pack. This helps us to size the motor. This is saying that a 50 kilowatt motor is not going to be big enough, but a motor rated at 100 kilowatts may in fact be big enough to at least almost accomplish the US06 objectives. And just a very small percentage of the time we don't accomplish the objectives. So there's a trade-off then when you're designing the vehicle of how big do I make the motor and associated electronics and so forth. and how much power, how much performance am I going to get. And this says I'm not going to give up much performance if I design the motor a little bit smaller for this drive cycle. Also, we might be interested in this over here is a scatter plot that shows the torque versus RPM usage points of the motor. So at every point in time, there's a certain motor torque and a certain motor RPM. I take those two pieces of information and plot a dot. And we see that I've also drawn on the limits of torque versus RPM for the motor. So one thing we see is that the simulation is obeying the limits. I'm never going outside of the limits, so that's kind of a sanity check to see if the simulation works. But this is also helping me to see whether the motor is properly designed or not. If all of my data points were right up here, then there's something wrong with my gearing ratio. My motor is operating at its max speed too much. Now the US-06 is a pretty fast drive cycle. It tops out at about 75 miles an hour. So we see that there are quite a few data points in the high speed region. If we simulate some of the other profiles, like a city profile, we actually see more of the data points over here than the lower speed region. We want to see, are most of my data points maxing out the torque? And here they're not. So that's good, because if I'm maxing out the torque all the time, that means my motor is probably under-designed. But if I'm way too far away from the max torque, that means my motor is probably over-designed. And here we see something that's like, well, it's kind of in the middle of the road. I'm not really maxing out the torque very often. I'm kind of maxing it right about there, is about the only time that I see, and I'm getting close in a couple of other places. But most of the time I'm staying away from the actual boundaries of performance, but I'm getting close. So that seems like a good design to me. So these are just some of the results we can use in sizing the motor, the battery pack, the electrical systems, and so forth. I'm going to pause the video here and resume in just a second. I'm going to jump to the code just to introduce you to how the code is organized without spending too much time in it. But you will be using this in one of your projects for your homework, so you might be able to benefit from the discussion. I'd like to spend the next few minutes showing you the structure of the code that simulates an electric vehicle. And as we mentioned before, there's two major portions to this. One of them sets up the vehicle, and the other one runs the actual simulation. So the first one is set up some vehicle. It sets up the vehicle and calls the M file that does the simulation itself. Here I'm going to make some variables global inside of my function just to make it easier to set things up. So I'm going to have a data structure called a cell, a module, a pack. These describe the battery. Something called motor, drivetrain, vehicle that describes the rest of the vehicle, the drive cycle, and some results. The drive profiles that are going to be simulated here I define as the names of the data files. The data files are text files. They're two columns. The first column is time. The second column is the demanded speed. To set up the Chevy Volt, in quotes, again, this is only approximately a real Chevy Volt, we first set up the type of cell that is being used by the battery pack. And there's a procedure down below called setup cell that puts data into a structure. And the data that we're putting in, we put in the capacity in ampere hours, the weight in grams, the voltage max of the cell, the nominal and the minimum voltage of this cell. All of those get determined. So the Chevy Volt uses a battery cell. It's about 15 ampere hours, about 450 grams. 4.2 volts is max, 3.8 is nominal, and 3.0 is minimum voltage of this cell. All of that information gets passed in the procedure. The procedure sets up the data structure and returns the thing called cell. Now we're going to set up something called a module, a data structure called module. which has the number of cells wired in parallel, the number of cells in series in a module, the overhead of a module by weight, as a fraction of the total cell's weight. So when we set up the module, there's 3 cells in parallel in a Gen 1 Chevy Volt. There's 8 in series in a module, at least in our model there is. And we're saying that there's an 8% packaging overhead. So the module is, I take all of the cell weights, add them together, and multiply by 1.08 to get an overall module weight. All of that stuff is going to get put together, and I make a data structure called module. So you can see we're building something up step by step. This cell is part of the module. Now we set up a battery pack, which is a number of modules in series, and then the overhead of the pack by weight, and then the SOC range used by the vehicle, and the efficiency of the module. So there's 12 modules in series, meaning there's 96 cells overall in series in the Chevy Volt. So 96 series, 3 in parallel for a Chevy Volt Model 1. And we're saying there's about a 10% overhead by weight in the packaging. And we're using states of charge between about 75% and 25%. And there's a 96% efficiency, energy efficiency of the module. So the module again becomes part of the pack, and we're building up overall how the vehicle works. Next thing, we set up the motor, and we're assuming an AC induction motor with characteristics that look like this. So L max is this number here. RPM rated is that speed. RPM max is that speed. The efficiency is given, and then the inertia of the motor is also given. So here we're saying 2,700 Newton meters, 4,000 RPM, 12,000 RPM, 95% efficiency, and about 0.2 kilograms per meter squared is the inertia. That's our motor. We're setting up a wheel, so the overall radius, this is the rolling radius of the wheel, the inertia of the wheel, and the rolling coefficient of drag. So those are input there, and we get a wheel data structure. And then we set up the entire drivetrain. We give an inverter efficiency, what is the fraction of the braking that's done by regen as opposed to friction brakes, what is the gear ratio, what is the gear inertia, what is the gear efficiency, and then I also pass in the data structures for pack, motor, and wheel that we have already built up. So the overall drivetrain, here we're saying 94% efficient, 90% regen torque, ratio of 12:1, certain inertia and a certain efficiency, and then the 3 data structures we've built up. That's the entire electric drivetrain. And finally, the vehicle. How many wheels? What are the road forces? What's the drag coefficient? What's the frontal area? What's the weight? What's the payload, which adds on to the weight? What's the overhead power? And what is the drivetrain? All these things get passed in, and I get a vehicle data type. So everything I need to know to simulate the vehicle is in that structure. Then it's going to start the simulation. I first read the profile of desired speed versus time. I simulate the vehicle. This number here is the grade, and 0.3 is actually quite enormous. We can put in different values there for the grade to get different angles. I think it's in radians. We can check that when we get to that point. If it's in radians, that's enormous. If it's in degrees, that's actually quite small. Or if it's in percent, that's quite small. So we'd have to check that when we get there. And then we calculate the range as we just talked about. It's the SOC range of the designed battery pack minus the SOC range from full to where we ended our simulation. So this is the first time we use the results data structure to see what was the ending battery SOC in our simulation. And then we print the range and so forth, and that's it. The rest of this particular file includes the functions that set up this cell, and you can see how it's done, and it's really fairly simple. We just plug the individual values into a data structure. So cell.capacity is capacity, cell.weight is weight, etc. Sometimes there are some computations. So cell.energy is Vnom times capacity, and cell.specific energy, etc. All of these are calculated. So we set up the cell, we set up the module, we set up the pack, and we set up the motor, we set up the wheel, we set up the drivetrain, we set up the vehicle, and all of these things are put there, and we're done. Now, it's just a matter of programming style. Why I did it the way I did it. I kind of like the details to be distinct from the ideas. So the ideas are up front is, oh, I'm making a data structure that describes a cell, module, pack, drivetrain, vehicle, done. The details of how we do that are important, of course, but if I put all of this in line, it would become a little bit difficult, I think, to read the code. Again, it's just a matter of style, and different people have different preferences for that, so feel free to adapt this code as you like. Here is the code that actually does the vehicle simulation. So we give it the vehicle data structure that we just set up, we give it the profile of speed versus time, and we give it the grade, and it gives us as output results. And some of these things are just pass-through results. So the results.vehicle is set to the vehicle, so I can just save results to a data file, and a year from now when I load that data file I can remember how the vehicle was set up and remember what drive cycle I implemented and so forth. The grade is road grade in percent. So I take back what I said before. 0.3% is a very shallow road grade. Standard road grades for highways in the U.S. go between about 0 and 8%. And some of the off-roads can go up to maybe 12 or 15%, but rarely more than that. So if you give a single scalar for grade, then that grade gets repeated, first converted into radians, and then repeated over the whole drive cycle, so every time step has the same grade. Otherwise, we could have a different grade for every time step, so I could be going up and down, for example. But again, I'm converting degrees into, or percentages rather, into radians. Most of what we're doing is we are converting first the profile of speed versus time is usually given in miles per hour, and we're converting that to metric because all of our equations are in metric. So I convert to kilometers per hour, and then I also can limit the desired speed to the maximum vehicle speed. But then what I'm doing is I'm just making a lot of zeros. I'm making a lot of storage for results. So because in MATLAB, if you resize a vector in the middle of a loop, it takes a lot of time, very, very slow. So I'm just making a lot of space pre-allocating for my results, so it makes for a faster simulation. I'm setting a previous speed value, a previous time value, a previous motor speed, a previous state of charge, and a previous accumulated distance, and then I go through a loop. And in this loop I do desired acceleration force, the aerodynamic force, the grating force. I get my rolling grade force, my demanded torque. I do some torque limiting. I look at whether I'm doing regen or not, and so forth. I compute acceleration forces, the actual ones. I'm computing actual accelerations and motor speeds, and I'm doing some limiting, and I'm then getting my actual speed for my vehicle and my actual distance so far. Then we're going to do some things with the battery pack, so I'm looking at the demanded power, the limited power, the battery demanded power, and computing then the battery current and the battery state of charge. All of these equations hopefully are exactly the same as what we saw earlier in the notes, and you can verify that. If they're different, please let me know, because I would like to change them so that they are both correct. And then that's it. We go through this loop, and when we're done with the loop, we're done with the simulation, and we return everything in the results data structure. So if you go back and you look at the results data structure that we initialized, there's a lot of information. We have desired acceleration forces, arrow forces, roll rate forces, demanded torque, max torque, limited regen, limited torque, motor torque, demanded power, limited power, battery demanded power, current, battery SOC, acceleration force, acceleration, motor speed, actual speed in kilometers as opposed to meters per second, and actual distance in kilometers. So all of those things are returned as a result of the simulation, so you have a lot of information that you can examine and plot and really understand at a very deep level what is happening inside of the battery pack, inside of the motor, and that will give you some insight into whether you are over-designed or under-designed, and what factors of the design might need to change in order to make the entire vehicle work the way that you would like it to work. So that is one example of simulating a load, a realistic load for a high power, high voltage battery system. If you are looking at a different application like frequency regulation or grid storage or something like that, you would have to come up with a simulator for that environment as well, instead of electric vehicle simulator, to see if your battery was sized appropriately. In any case, it's something that can be done. I have time only to show this one example here, but I leave it up to your imagination to come up with many different types of examples as well.